Second gas law that we're talking about is called Charles' law, and again you can see the demands that are associated with Charles' law are listed right here on page 156. Charles' law is a relationship between temperature and volume. For Charles' law to be used, we need to always use temperature in Kelvin. So every single time that you see temperature in our gases unit, you're always going to switch it into Kelvin. In Charles' law, what we are assuming is that pressure and mass will be constant. Charles' law is a direct relationship, and what that means is that if temperature is going to go up, the volume is going to go up as well. And if temperature is going to go down, the volume will go down as well. Charles' law says as the temperature of a gas increases, the volume will increase as well, as long as the pressure and the mass are constant. The equation for Charles' law is going to be V1 over T1 is equal to V2 over T2. This is showing Charles' laws in images, and you could kind of think about here a balloon. So if I put the balloon over top of the fire, what will happen? It's kind of a moderately inflated balloon. If I put the balloon over the fire, what happens is we have a higher temperature. With that higher temperature, if we think of kinetic molecular theory, the molecules are moving faster. When the molecules are moving faster, they are going to expand. They need more space. They have bigger spaces in between the molecules, and they're going to expand, which leads to a greater volume. If we were to take the exact same balloon, and we were going to take it off of the fire, because we are lowering the temperature, the molecules would not be moving as fast, they would not have as much space in between them, and therefore we would have a smaller volume. And again, this is a direct relationship, which means that when one is going up, the other one's going up, and when one is going down, the other one's going down, when we're talking about temperature and volume. This is showing Charles' law graphically, and what you can see is that as the temperature increases, the volume is also increasing as well. If you take these graphs and you extrapolate them, which is what these dotted lines are here, the extrapolation of temperature and volume graphs meet at absolute zero, which is 0 Kelvin. This is a Charles' law example, and the first thing that we have to do is pick out our variables. A gas inside a cylinder with a movable piston is heated to 315 degrees Celsius. The initial volume of gas in the cylinder was 0.3 liters and 25 degrees Celsius. What we're looking for is the final volume, which means we're looking for V2. And what we started with was a volume of 0.3 liters. And then your temperatures, you'll see I've already picked out. Our temperature 1 is 25 degrees Celsius. In order to turn it to Kelvin, we have to add 273. And our temperature 2 is 315 degrees Celsius, which we have to add 273 to as well to turn it into Kelvin. What I'm looking for in this example is V2. And what that means I have to do is get V2 on one side all by itself. That means I have to get rid of T2. In order to get rid of T2, I'm going to multiply both sides by T2 because right now T2 is being divided. And what that does is it crosses off T2 on the right. So we end up with V2 is going to be equal to T2 V1 over T1. Now we have to sub in our numbers. To get our final answer here, we're going to do 588 multiplied by 0.3 liters divided by 298. And our answer here will be 0.59. And what we have to do is we're taking the answer that was given to us in the question, or sorry, the number, and we have two significant digits. We're not going to include our temperature in our significant digit calculations. So we're going to keep two significant digits, which means 0.59, and the units will be liters. You'll see that based on unit analysis, the kelvins are disappearing and we're ending up with liters. The last thing to talk about this law is that if I am looking for temperature at all, if that is my missing variable, then what I need to do is I need to get temperature on the top before I can solve for it. So if I were looking, for example, for T1, what I need to do is I need to get T1 on the top. So I'm going to get T1 on the top by multiplying both sides by T1. That gets rid of my T1s on the left. And now I have to get T1 by itself on one side, which my second step I'm going to do in blue, which means I have to get rid of T2, multiply both sides by T2, and that gets rid of T2 on my right. Then I have to get rid of V2 by dividing both by V2, which gets rid of V2 on the right. And over here in black, what I'm left with is I have T2 V1 over V2 is going to be equal to T1. If you don't do that, you would get the incorrect answer because you would have an answer of 1 over T1 instead of T1 on the top. So it definitely has to be on the top before you can put in your numbers.